All right, my friends, I know what a square root graph looks like, the basic shape. I know what happens if you double it. It's just a vertical stretch. So I'm just going to draw basically that shape from 4 to 9. So if I put 4 in, I'd get 4 out. If I put 9 in, I'd get 6 out. So the part of the graph that we're thinking about here would be that little snippet right there. Okay, now if we're revolving it around the line x equals -2, I'm going to take these numbers off real quick. Okay, well, good times. Okay, so it looks like I've got about 6 units there. Whatever. Something. Okay, my friends, so here's the surface that I'm trying to find the area of. Okay, no big deal. We're just going to add up infinitely many, infinitely thin rubber bands. So getting started on that, I think I'll go ahead and draw like kind of one in the middle. I don't know why I feel like I always need to do that. I'll make it kind of give it a little bit of width there. There we go. Okay. So let's find a formula for that. Okay. So our plan, my friends, is to do volume is equal to, not volume, good night. Surface area is equal to, and we're going to do, let's see, 2 pi times the integral from, now let's think, is this going to be a dy or a dx? Which axis do we need to be scanning to be accumulating these rubber bands? Okay, and so I claim that this is going to be need to be a dy setup, and that's going to help me know how to set things up. Okay, so my plan is to figure out what's the radius in terms of y, and then to have basically the appropriate arc length formula here. So we're going to do 1 plus f prime of y squared, like so. Okay. All right. So getting started on that, let's see, y is equal to 2 root x. If I do the derivative now, I'll get f prime of x. And so let's solve for x first. So you could divide by 2 and then square both sides. I'll just write it as 1/4 y squared. And then that way, dx dy, also known as f prime of y, would equal 1/2 y. There we go. Okay. All right, so now we'll know what to put in for f prime of y. Now let's figure out what the radius is. This is typically the trickiest part. So, and we need the radius to be in terms of y. Okay, so a couple of questions. Let's break this down. So first question, what is the distance of this is part of the radius, the distance from the x-axis over to the graph? Well, I claim that that part would equal f of y, or your x coordinate, aka f of y. And then you need to add this distance right here. And so that distance, my friends, would be 2 units. So that entire radius should be f of y plus 2. Okay, so I'm going to make some notes here. The radius is f of y plus 2. Whoops. Oh, not written like that. Good night. Don't write it like that. That would mess everything up. Okay, there we go. Is f of y plus 2. Okay, so now moving on from there, our surface area would be 2 pi. What kind of bounds would make sense? We're doing a dy integral. And so I hope it makes sense. We're going from 4 to 6 on the y-axis, even though I erased that. The radius, we would have the quantity f of y, which f of y is, where's f of y? Right here. Is 1/4 y squared plus 2 for the radius. Then we'd have the square root of 1 plus, we figured out f prime of y, that's right here. So we'd have 1/2 y squared dy. There we go. Okay. All right. Totally up to you how much you want to simplify this, or if you just want to smack that thing into your calculator right now. Either way, nobody really cares. And it looks like we get the integral piece is 45 something something, and then when we double it, we get about 91.371 pi, and then it's surface area, so units squared. Multiplying pi in would give us approximately 287.050 units squared. There you go. Okay, so when y equals 7, so same exact region, this time we're revolving around y equals 7. Let's see, so put 4 in, we got 4 out. Put 9 in, and we got 6 out. So here's our region. And then here's y equals 7. And so when we revolve that around, let's see, that's 3 units, so about there. Go. Okay, so I'm going to draw one of these typical rubber bands, kind of adding a little bit of width to it. Oops, or a lot of width to it. Anyway, it's symbolic. Hopefully you know what I mean. Okay, so we just need a formula for that, and then we'll pop it into the appropriate surface area formula. So surface area is always 2 pi times the integral from a to b. I hope it makes sense. This time we're accumulating these rubber bands as you scan the x-axis. So we're going to the dx integral. So I'm just going to go ahead and pop those bounds in right now. So we're going from 4 to 9. We need something that represents the radius and then the arc length. And the appropriate arc length formula would be 1 plus, in this case, f prime of x squared, and then with respect to x. Okay, so trickiest part, figuring out the radius. I'm hoping if you look at your picture, it should help you keep that straight. Okay, so let's look at that. We've got the radius would be this distance. So let's look and see what we've got at our disposal. So a couple questions for you. What is this distance in terms of x? I claim that that distance in terms of x is f of x. And what is this distance? Right, that's 7. And so here, I'll make that look more like a 7. I don't know. Or less like a 7. I don't know. Anyway, so what would the radius be then, my friends? I hope it makes sense. The radius in this case would be 7 minus f of x. There we go. Okay, so this right here would be 7 minus f of x. Okay, all right. Now let's just kind of put everything in. First of all, f of x is equal to 2 square root of x, and then we'll need to know what f prime of x is. And so that, since f of x is equal to 2 root x, you could just use power rule on that and end up with, what would that be? 1 over square root x, I think, right? Because 1/2, yeah, okay. Anyway, so then we'd end up with a setup of surface area is 2 pi times the integral from 4 to 9. The radius would be the quantity 7 minus 2 square root x. And then the arc length would be 1 plus f prime of x is 1 over square root x. And then you could see squaring that out might be a good idea before you bother punching it into your calculator, just to have fewer things to keep track of. Anyway, make sure that you can punch that into your calculator and get your answer. You're not forgetting that 2 in the front, for example. And all right, my friends, so punching the integral part in on my calculator, I get 10 something something. I'm going to go ahead and double it for that 2 in front. I'd end up with approximately 20.9, it's like 40 pi, which then in turn is approximately equal to 65.785. Either way, what kind of units would it be if it's area? And I hope it makes sense. It would be square ones. There we go. All right, my friends, let me know if you get a different answer for that one. For some reason, I am just the sloppiest person with a calculator ever. So I wouldn't be surprised if you get a different answer than I did when you calculated that. Let me know if there's any problems there. All right, but hopefully the concept of how to set them up, how to decide what your radius is, the fact that we're just adding up a whole bunch of 2 pi radius times arc length type stuff, hopefully all that makes sense, okay? All right, here is some information about your upcoming test. Please be prepared for the format. There will be 6 multiple choice questions where you are to provide solutions on your scratch paper that shows how you did it without a calculator. And then there is 1 College Board style free response problem where you will just set up clear integrals on paper and then make your calculator do the rest of the calculations. So please be prepared for that. Let me know if you have any questions about it. All right, my friends, I hope this is all making sense, and I hope you ask questions if things aren't. Take care, everybody.